Okay, all right. Assalamualaikum and very good day to all. So we meet again in our online lab sessions, and in this evening, I would like to give some briefing regarding our previous lab exercise, which is on the Huffman coding. Okay, and I need you to download this file and already in the column. Okay, and Dr. Sharenti already gave a very step-by-step process in this example, especially on the Huffman coding. Okay, so what you need to do is that you need to understand regarding how you can develop the trees. Okay, especially for binary trees for the Huffman coding, and then you need to specify, you need to calculate the how many message size for the given message actually. Okay, so basically the question is very straightforward. Okay, it's similar like we have in the example in the slide or in the video recorded by Dr. Soyanti. So you are given a patterns here. It's a string of patterns here that consists of several character. Okay, and each of the character here we can have multiple of character. Meaning that we can have a duplicate. Just imagine that you have a file, and you have uh, a wordings or paragraph, something like that, and then you want to transfer this file into the someone else using an email, but it will be through the network transmission and so on. Okay, so Huffman coding is one of the algorithm, uh, mostly on the lossless data compression actually, and it can be inside the image compression, how you can reduce the size of the image, or you can reduce the size of the file. Okay, more general is on the file itself. Okay, instead of we can save the file 1 MB. Okay, we can send the same file to the other person through the network, maybe around 500 kilobytes only. We can reduce at least 50% the size from the original. So this is the purpose of the Huffman coding here. We want to reduce the size of the message that we have here, but we still keep the original file. Okay, so we have a numbers of character here. We have a G, F, F, A, C, D, D, until the last character here is A. So based on the steps given from the video, so you need to count the frequency of each unique character. What I'm meaning about unique character is that, okay, so how many the character for G? Okay, so you need to count it one by one. So for example here, let's say we try to do it together. So if I'm doing mistake, or if you want to participate this session, okay, you can type down in the chatting. So I know that you are following my question. And let's say G here, we have how many G we have here? One, okay, two G, right? Here we have two. So and then continue again for the second character, right? So for the second character, we need to count from this message F, F1, 2, 3, and so on. Okay, so this is the thing that you need to do. The first thing is you need to what you call count the frequency of unique character. Okay, so what the meaning of unique character is that we don't call FF here is unique because it's duplicate. The unique one is only you need to count only one character, but the frequency of that particular character. Okay, then you continue again with the other character. Let's say for this one is A is equal to what? Okay, let's say 1, 2, 3, 4. You have 4. Okay, and then etc. and so on. Okay, so this is the thing that you need to do. First thing, to identify, right? So once you already identify the frequencies and also the unique character in this message, then you need to do the, what you call, you need to use the Huffman coding steps in order to get the binary and also get the code of the message here. Last thing that you need to do is you can calculate the message size based on the bits in the code work and also the frequency of that particular character. Okay, so this one is this lab exercise. Okay, so I would like to give you some example of the Huffman coding. Okay, instead of given by the Tosorianti, it may help you to understand more detail what is between this Huffman actually. Okay, just try Google up in the Google search and so on, and found out this one is may be useful for the students. Okay, that's why I want to share this knowledge for you. Example I have here is come from the one website. Okay, let's say we have a numbers of character. Okay, is A, B, C, D, E, and also F here, right? And then each of a unique characters that we have in this table here, they have frequencies. Okay, in frequencies. Imagine that this is in one file. Okay, and that's why the example here in thousands. Okay, we have 45,000 of A character in a file, 13,000 of character in a file. Imagine that in one file we have 45,000 of character A. Okay, compared to what we have here, we only have two characters. We have four characters for this particular message, but we have here in terms of we use a simplicity in this table in thousand. Assume that we have 45,000 A, 30,000 for B, 12,000 for C, 60,000 for D. Last character is F, so it's only 5,000. So what is happening here? Okay, so this Huffman coding, they have two variations here. The first one here, they have we're using a fixed length code work, right? So in a fixed length code work here, we does not sort the frequencies increasingly. Okay, so what I'm meaning is that we only get whatever that have in this table to become a binary. Okay, for example, starting from the character A and also character B. Okay, so in the previous video given by the Serenity, we try to look on the minimum frequency, two minimum frequency that we have. Then that one is based on the variable length. Okay, so we try to look on the variable length minimum frequencies. Okay, for the first one here, I want to highlight, try to give you some this one first, and then this one will be covered later. Okay, let's say we have this one 45 and 13, so we need to take two nodes, okay, that contains the frequency from this side and also this side. Okay, 45 and 13, we count it together to become a new node, which is 45. Okay, this one, so 45 and also 13 here, we take these two and then we sum together these two frequencies from node A and also node B. 45 plus 13, that will be 58. Okay, so we're done for this one. Okay, the next step is, once we have these two nodes already done, and then we have some kind of, this one we call as the, okay, in internal notes. Okay, internal notes. This one is notes. Okay, A and B here. This one is internal notes. Next step, we need to calculate the frequencies of two notes of C and also D. And both of the frequency are 12 and also 16. So we have 12 here and then we have a 16 here. We sum two frequencies from two notes here to become a new note. Okay, so we done for this one. Okay, and then this one also we call as a internal notes. Okay, so the last one here. So since we have a 9 and also 5 here as a last, what we call last pair of the notes here. Okay, we count it together to become 14. All right. So since this 45 and also 26 here are the internal notes that are side by side together. Let's say I want to jot down here is this one is 58. Okay, this one is 28, and the last one here is 14. Okay, so the next step here, we need to find a pair as well. Okay, for this 58 and also 28 to become a new note. Okay, we calculate together. 86 is the summations of the 58 and also 28, which is come from the internal notes of A, B, and also C, D. Okay, and the last one here is 14. Once we have here 86, okay, we need to count it by this one. The last internal notes, that summation of character E and F equal to 14, and we have 100 of frequencies. Is total of to be specific is 100,000. Okay, this one is 100,000. All right, so we have here a fixed length of code work. Okay, and then we need to specify what we call the marking the binary left and also the right nodes. Okay, so all the edges here, this one we call as the edges. Yeah, this one is we call as the edges. Okay, I want to use different color here. Orange. Okay, so this one we call as the edges. So anything the left edge here is we set as 0 bit. The right edge is equal to 1. Okay, so what is the code word? Okay, or the other things is what is the code that represent A, the character of A? Okay, the code starting from the root here is 100. A is here, directly here. Is we read like it 0, 1, sorry, 0, 0, and 0. 0, 0, 0. So we have 3 bits. Okay, 1 bit, second bit is third bit. We have 3 bits. Similar things to the others character as well. Let's say, for example, B, 0, 0, 1. Okay, so then we continue again. Continue until at the end of the character. Let's say I reach on the last character. Here is F. We have 1, 0, 1. 1, 0, 1. Okay, this one is 3-bit also. This one also 3 bits. Okay, so whenever we have this code work, okay, and also numbers of bit for each of the character, okay, actually we know that by using the fixed code work here, we still remain the size of the file, even though we already reduced number of file, but it's still keeping each of the character are 3 bits. This one is 3 bits, this one is still 3 bits, and then this one is 3 bits. Okay, so we have here like another table. Okay, it's another table that represents, okay, I just 0 0 1 sorry, 1 0 1 1 0 1. Okay, so the constructed tree that we have from this diagram here, we can have 0 0 0 0 0 1. Let's say last character is 1 0 1. Can you see here, based on this example given in this table, okay, the fixed length of the code word in this table, okay, all the size of these bits are 3. This one is 3 3 3 3 3. Okay, so the aim, or we can say that the objective of the Huffman coding here, we want to reduce the size of the file. Okay, even though we have here, we still reduce instead of by using 8 bits. Okay, okay, imagine that one character is equal to 1 byte. Okay, and then 1 byte is equal to 8 bits. Okay, so imagine one character is equal to 8 bits. Now we don't have any uh, compressions by using any algorithms. Okay, if we took on this one is 45, we will have 45 times 8 bits. Okay, for character A, and then we have some amount for it. So if we do something that is all the things are 8 bit, let's say assume that we have one 1000, this one is equal to 1 million. Okay, which is equal to 1 million. Compare that we have here. Let's say example, this one is equal to 300, right? 300k. Okay, equal to 300k. Okay, so the thing is that instead of using a fixed length code work here, we can use another thing that we call as a variable length code work. So this variable length code work, okay, actually will reduce the numbers of bytes, sorry, a number of bits compare if we are using fixed length code work. Okay, so what is happening in this variable length code work here, right? So we need to find, okay, we need to identify the minimum frequencies from this table. So we need to find two minimum frequencies. Okay, so based on this table that we have here, so which are have the minimum frequencies? So we look on this one, is it 13, 20, 12? No, it's 9 and also 5. Okay, this one, these two, 9 and also 5. Okay, so 9 and 5 here belongs to character E and belongs to the character F. So we take out these two nodes and we create a new node that represent a summation for these two frequencies. Okay, so we have here 9. Sorry, okay, so 9. So we have here a minimum. So whenever we call a minimum here, we need to sort it into the increasing terms. Okay, so 5 will be the first one and 9 will be the second one. Okay, remember that in a binary, if we have a sorted binary, we need to arrange the numbers increasingly. We don't put 9 here. Okay, we don't put 9 here and then 5 there. Okay, so we cannot together. This one has become a new internal node that represent a summation 5 plus 9 is equal to 14. Okay, so this one we already have this one. Now we need to find, okay, among the others frequencies, this one that have a minimum, at least two minimum frequency. Which one? Either 16 and 12 or 13 and 45. No, the two minimum is this one, 13 and 12. Okay, we take out these two frequencies that belongs to character B and also C. Okay, let's say I want to put it here. So we need to arrange the trees 12 first, and then we have here is 13. We count it together. This one has become an internal node is equal to 25. Okay, so right now, just now we have 14 here. Okay, and then this one we have 25. Okay, as an internal node. So right now we have 45, 25, 16. Okay, we still have another frequency here. This one is 45. We have 16, we have 25 and 14. Okay, so based on this, what we call the frequencies here is updated frequencies. So the process is keep repeated again and again. Okay, we need to find two minimum frequency again and again. So imagine that we have here let's say I want to have here 45, 25, 16, and also 14. We have four remaining frequencies. Okay, we have 25, 16, 14, which are two minimum frequencies. 12, sorry, 16 and also 14. So we take out this 14 and 16. Okay, we take out these two. Can I put here 14 and 16? We sum up together here as equal as 30. Okay, now we have these three. Okay, so the last one here, either we sum up together, this one is become 30. So we have 45, 25, and 30. So we compare together all the frequency that we have here. Is it 45 and 30, 30 and 45, or 25 and 30? So we keep searching for two minimum frequency, which is 25 and 30 are the two minimum frequencies. Okay, so we take out 25 and we take out 30. We sum up together, this one is equal as 55. Okay, right, and the last one will be 45. Since this one we already updated, for two frequencies, we sum up together is equal as 100. So right now we have what we call the frequencies that can be matched together to become as a binary tree. Okay, so that's why, as we have in the diagram here, okay, this one that represents all the nodes and also trees that we have from here, this one and this one as well. Okay, so we have the last one here is equal to 100, that belongs to 55 and also 45. Okay, so now we have what you call a tree, a complete tree that belongs to this one. Okay, can you see here, if we compare together uh, between variable length and also fixed length, okay, fixed length here, 45 we still put it in the left side, okay, because we do sum the variable length here, but the level of the trees here, the level of here, we keep only one level, but this one we still have three level. So this level represent how many bits that can be counted for the message size. Okay, for A we need to count only one byte. Okay, sorry, one bit. This one is one bit. Okay, 45,000 we multiply by one bit, we still keep 45,000. Compared to if we have here is A, okay, we have 3 bits. In order to represent A character by using the code here, we're gonna use 3 bits. 3 times 45 is equal to maybe around 100 something. Okay, 100. Compared to we have only remain 45,000. So we reduce the numbers of size. It's a lot. Okay. Let's say for example C. Okay, C. How many level we have for this one? 1, 2, 3. Okay, of course we still keep the C here for. And but we add another bit for F and also E. 1, 2, 3, 4. 4 bits. Okay. So more detail on the table here for variable length can be seen in this one. Okay, this one. So we have A is only one bit. This one is 3 bits, 3, 3. We have 4 and also 4. If we counted something like this one, we might have something around 2044K, something like that. Okay, so by comparing to the fixed length code work and also variable length code work, we reduce maybe around 20 to 25%. Is a lot. Okay, so when we do some comparisons here and we remain the original size, the original message in the file, okay, is very helpful in order to keep our data storage is large enough. Okay, and then we can put more files later. Okay, right. So this is one of the example that I want to share with you. Okay, comparison between the fixed length and also the variable length. Okay, so what we have here, we need to focus on the variable length. Okay, right. So variable length. So how many size that we have for this one? Okay, how many size that we have? So according to the video that provided by Dr. Suryanti here, all right. So you need to keep the frequencies for each of the character, and then you need to count it again based on the length of the code work that represent the numbers of bits. Okay, multiple by this one. Okay, for example, we have A, the frequencies is 45. Okay, 45, and the code that we have here is 0. So the size for A here is, you need to count it, 45. The numbers of frequency for the character is multiplied by 1 bit. This one will become 45 Okay, 45 bits. 45. More specific is 45,000. Okay, so let's say for B, how many frequencies is 13? Again, is 13. So the code for this one is 101. Sorry, 101, but it's still the size of the bit here is 3. So 13 multiplied by 3 is equal to 39. Okay, it's 39. C, let's say for example, C is 12. Okay, so 100, we still keep the 3 bits. 12 multiplied by 3 bits is equal to 36. Okay, this one is K, K, and so on. Let's say example here, the last thing that you need to have here is this one. Okay, you need to do some calculations. There are 3 calculations in order to uh, the message size of this one. Okay, so we still keep what we call the reference size. Okay, so what the purpose of reference size here? Because whenever we do some we call this one as an encoding, encoding. Okay, encode. Okay, we represent this one into a compressed version. Okay, so we need to do some decoding. Okay, in order to represent into the original part. Okay, so that's why we need to have some reference size, and this reference size will keep what we call encoding procedure, something like that, to be kept as a message size. Okay, now we go back on the example on the lab exercise that we have here. Okay, right now, and you need to use Huffman code, and then you need to show the process of encode a message. Okay, step by step. At the end of this question, number 1, you need to calculate the message size. So this is the aim of these questions. Okay, in order to get this message size, you need to show me the process of the encoding. So question number 2 here, you need to find a code that implement Huffman code. Okay, meaning the coding. The output of your code must similar with question number 1. Wherever you have the answer in question number 1 here, you still keep what you call the tree similar what you have in question number 1. Just like I have a tree in this one. Okay, this one. Okay, and then it will show you uh, the code word of the message. Okay, I have a sample code here that I have found in the internet, over internet. Okay, and then you can find it in any sources. This one is a Huffman code available in one of the websites. Okay, so what I'm doing here, I'm do some modification, especially in the input character and also the frequencies here. Imagine that I'm using the same character as in this example. Okay, A, B, C, D, E, F with the frequencies 45 until 5. That is why I put it something like this one. A 45, B 13, C 12, G 16, E 9, and F is 5 frequencies. Whenever I run the program, so you will get this kind of output. Okay, so this coding using the structure, using a structure and also functions, that you may look on the detail of the coding, how the process of Huffman coding is implemented. Okay, for example, here is character A is the code is 0, B is 100, B is 101, and if we look side by side, okay, the output of the program Huffman coding, by using the same character as in this example, we still keep the same output. Okay, so for example, A is 0. Okay, this one is 0. B is 101. Okay, B this one 101. Okay, is 101. C is 100. Okay, we don't call it 100, we call it as a 100 because we call it this one as a binary. D is 111. Okay, so E is 1101. Okay, yes, of course, you still keep them what you call the same message if we do manually, and then we do by using the coding. Okay, right? So if we do manual for the fixed length, so this is the diagram and also the code for the fixed length code work without any, this one we call it without any minimum heap. Okay, so normally Huffman code we're using a minimum heap in order to reduce again the number of sites. Okay, and then it keep repeatedly finding the smallest minimum the smallest two frequencies from the table. Yeah, so we go back on the question again. Now you need to analyze your answer by providing the following questions. So you need to answer these questions. So how much Huffman code able to reduce the message size? Okay, as I mentioned just now, okay, the Huffman can be reduced 20 to 25% based on the message that we have. Okay, for example, this one, so Huffman code can reduce almost 20 to 25%. Okay, so but not for this example. Okay, you need to count, okay, manually, right? Let's say, mm, what is the example? Let's say the original size is equal to 120. Okay, after we do the Huffman, uh, either we use a fixed or variable length, we can read the size of it like say 60. Okay, 60. So we can calculate this one. I mean, how many read how many this one? Okay, 60 over 120, we count it 100%, something like that, and then we can reduce 50% or almost percent of the original file, but we still keep the same, or we call the same contents itself. Okay, and then you need to find out how efficient greedy methods in Huffman code. Okay, and based on the code that I found out here, okay, let's say I found this one. Okay, so you need to count the time complexity of the code. Let's say you found out this one. Okay, so this one is 1 1 1 1 1 and so on. We count it together, and then how many that we have. Let's say we still have four loopings inside here. Either we have a square root, uh what is it, huh? Okay, let's say we have, what is it? I just found it. Okay, for example, we have a looping. So what is the frequencies, or what is the time complexity for the looping here? This one as well. Okay, you already look on this one in the previous, especially on the first week on the syllabus. All right. Okay. So now I already give you some briefing regarding this one. Okay, so I would like you to answer this question, okay, as your exercise, and you need to submit the exercise in a column